Okay, let's look at problem 411 in the book. This is the Maclaurin series of cosine of x. So here's the deal. You're going to see this, and cosine of x is 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. This statement in and of itself is not terribly helpful. You're going to have to come up with some form like this. You can kind of figure this out from here, and sometimes it's actually pretty straightforward. It's not too bad. Like e to the x, I think, is x to the n over n factorial, and it's pretty obvious to see that. However, this is not always as obvious, so from a practical standpoint and kind of real world, a lot of times I'll just look for the Taylor series expansion cosine of x, or of cosine, right? And you come in here, and this is a page that I often go to. You're obviously not going to be able to follow what I'm doing. It's just trying to show you that a lot of times I just end up looking for this on here, and it comes down to here. Here's a bunch of, so there's a sine of x, there's a cosine of x, and whatnot. So that's the type of thing. So I'm not overly hung up on having you have to figure out how to take this equation into this one unless it's really straightforward, and then you should be able to do it on simple ones. So given that we have this thing, what we're trying to do is we want to use a loop, and we want to estimate the value of cosine of pi over 4. Okay, and as it says, after each term is added, compute the true and the approximate percent relative errors, and then continue doing this until the approximate percent relative error falls below a criteria conforming to 2 significant figures. Okay, the way I do this is with a while loop. So let's come in here. First off, the first thing that you want to do on all your problems, you want to make sure you go through, and actually we'll even do this, they'll do this in a cell. This is the cosine, this is, oh, it's 4.11 cosine of x. Okay, so this is just, it's not magic. It just keeps from having residual weird stuff floating around in your memory space. So that's good, get rid of that. Okay, so now I'm going to, what I'm going to explain here is the process. So if you try to, it's the idea. If you just try to memorize this process, it's probably going to mess you up a little bit. So let's just talk about the idea. The idea is simply that we take the first guess. So the first guess of cosine of pi over 4 is 1, right? The second guess is 1 minus pi over 4 squared minus 2 over 2, which I don't know what it is. And the next guess is that plus this, and so on. So you're making every guess. So it's a loop. So let's just do a simple for loop. I can go for I equals 1 to, we'll do to 10 to start, right? And I'm going to say my cosine is equal to my cosine plus, so in other words, my current guess is my previous guess plus whatever this thing is right here. So I'm just going to write this down. I'm going to say minus 1. Okay, so that's annoying, so let's get rid of that. And I'll do this in terms of n, so it uses the same variables. Minus 1 to the n divided by factorial of 2 times n. You don't need that parentheses there. Right, all that times x to the power of 2 times n. Okay, so again, I've talked about this all the time. First pass, last pass. The first pass through here, n is equal to 1. But the problem is right here, n is supposed to be equal to 0. I did 1 because that's just totally habit. But this needs to start at 0, right? Now, my cosine is equal to my cosine. Well, my cosine is not defined, so let's initialize my cosine to 0. And we should be good to go. So, except for we don't have x. So, x is equal to pi over 4. And for giggles, we're going to say truth is equal to cosine of x. Okay, so then I'm going to come in here after I'm done. I'm going to say my cosine and truth. So I can see what they are. Boom, let's run that. And that's actually really close to being, so even with 10 iterations, you can see that we're really close to the same answer. So here I'm going to say format long G. So when I run it, I have a bunch of numbers here. And you can see I got accurate out to, wow. With 10 iterations, it's just, I don't know, this just this last point that's different. So that's extremely accurate. So lovely. Okay. So that is the simplest form of doing this loop. Nice and straightforward. It's a simple version of it. Here's the thing. That's lovely. But the problem is, how many points do I really need to do? Quite frankly, I usually will start off with something like that. So I can run that, boom, runs it, and you're going to find this is going to be accurate still to the same number. I'm not getting any improvement over that, right? So, but I just did 1,000 iterations. Well, how many iterations do I really need to do? Well, out of dumb luck, I did 10, and I found out that that was pretty accurate. So maybe I only need to do 5. If you're just doing a one-off, it almost doesn't matter. But since the intent of this is to be able to use in some grand program to do stuff, you don't want to do 1,000 iterations when you only need 4, and you don't want to do 7 iterations when in reality you need 190. So you need to figure out, how do I do this until I can stop, until I have to stop? When am I accurate enough? And that comes to this part right here. It says we're supposed to continue repeating the loop until the approximate percent relative error falls with a criteria conforming to 2 sig figs. Okay, so we talked about this. How do we do this? I'm going to say sig figs is equal to 2, and I'm just going to say 4 because that's too small. So what is my ES? My ES is what? It is 0.5 times 10 to the power of 2 minus n. So that is, now if my approximate error falls below this number, this equation is what it's talking about here in equation 4.7. That will give us the right thing. Now when I throw in this 2, it means I'm doing things in percent. If I don't have that, if I do that, then I'm doing things fractional. And since this one asks specifically for 4%, I'll do it in percent. Okay, so there's my ES. Now, inside here, I need to figure out what is my EA and my ES, right? Or sorry, EA and my ET. It says right here, compute the true and approximate percent relative errors. So the true is easy enough, right? The error true is the difference between what I'm currently guessing and the actual true value. So my current guess is my cosine, right? And the true value is truth. And I think maybe it's actually the other way around. Minus my... Turns out I don't care so much because I'm going to turn around and I'm going to take the absolute value of it usually anyways. But that is the true error, but that's what we would call ET. We want little ET, so we want the percent error, so we're going to divide by truth times 100. But please be aware of order of operations. Make sure you divide the whole thing by truth, not just the last value. And EA, what is EA? Well, EA is equal to the previous guess, so here it's previous minus current divided by current, right? Times 100. So what is our current guess? Our current guess is my cosine. Turns out you have to spell it right. My cosine. What is our previous guess? Well, the problem is right now we don't have it. So you'll notice right now there's nothing holding on to the previous guess. So the way I do this, what I find easiest is before I do this, I can say previous. I'll put previous, or I can put old. I like old. Old my cos is equal to my cos. So think through the logic here. So I'm going to initialize it to something. I'm going to come in here and I'm going to start my loop, right? And the first thing I do is before I change the value of my cosine, I'm going to grab the value, grab onto the old version, right? So the old version is this. Now I'm going to update it. I'm going to calculate the true error and calculate the approximate error. So the nature of this one is purely because we are dealing with stuff that we know the truth. This is an educational tool, right? If you knew the true error, that would mean you actually know the answer. And if you know the answer, there's no reason to be doing this. Except for when you're in school trying to learn this stuff, and then it's a good reference point. So you generally won't be able to do this, but you for sure can always do this. Okay. Now, I calculate that. The problem is if I run this, boom, I'm going to come in here and look at this. What did I forget? And so undefined function or variable n in line 5. Oh yeah, turns out I have to call this sig figs. Okay, now I'm going to run this. Previous, did I leave previous somewhere around here? Oh, I called this now my cosine. So run that. Lovely, there I have an answer. Okay, so now if I look at ET, it's a number, and EA is a number. Okay, so the problem with that is it's not particularly helpful. We want to track it as it's building up. So there's two ways to do this. The one way I'm just not even going to talk about. It's making this vectors as we go along. I don't like doing that because I think it makes it complicated and confusing, and it for sure, my opinion is that it makes it complicated. The fact is that it definitively makes it less efficient. And so what I'm going to suggest is that we kind of create a temporary variable that once we get it to work, we can get rid of that temporary variable, and it's a non-thing. So my temporary variable, I'm going to call it data. I'm going to say data is equal to data, my previous value of data, and this will make sense in a second. And then I can start putting my information. And my cosine, EA, and ET. I can't think of anything else that's really interesting to put there. Okay, so every time through here, and so that means up here I need to initialize it because the first time there is no data. So the first time I say data is equal to bracket, empty bracket. Okay, so this basically just initializes it. It says that it exists, there's something there. So the first time it's going to say data is equal to this, which is nothing, and it's going to put n, the value of my estimate, and the EA and the ET. And the next time through, it's going to say data is equal to whatever it was before, which we just did, and it's going to keep on adding and building up this table. So now when I run this, I can come in here, and I can look at data. Okay, I forgot, I'm doing 10,000. I back this off to 10 runs. I can look at data, and now I have the columns. At n equals 0, here's this, and here's this, right? And you can go through and see what it is. So there, I'm going to look at, format, short, G, data. So now you can look at n equals 0, my cosine is equal to 1, EA is 100%, and ET is minus 41%. And you can see the signs bouncing back and forth. So here's what's interesting is we can take this and let's plot it. So you can actually see what's happening. It's plot data colon comma 1. So we're going to plot against the iteration number, and data colon comma 2. We're going to plot against the actual current guess for my cosine. And you can see here it stabilizes pretty dang quick as to what it is. And we'll call this a nice red line, and we'll do a red star so we have some markings on it. And let's do a x label iteration and y label estimate of cosine of x. We can do pi over 4. So here's kind of cool. You can do a pi, that's a LaTeX command, over 4. I think we'll find out. And let's run that. And then here we have a nice little plot. So notice the pi symbol, that's what that \pi is. Now, if you want to look at it, if you actually zoom in on this right here, you'll see that it still moves around a little bit, but basically the cosine function is just really, really stable. So after just a few iterations, it pretty much locks in on its value, which is pretty impressive. Okay. So there we go, and we can plot EA and ET, this information. So there we go, we have a bunch of information. Now, the problem is we still haven't done what they've asked us to do, right? So the problem is they want us to continue doing this until the approximate error falls small. Okay, so how do we do that? So the way that I do not prefer, but it's totally reasonable, I'm going to come in here, and I'm going to put this up to a really big number. Because I'm going to come down here, and I'm going to say, if the absolute value of EA is less than ES, then break. That is what this is saying is I'm going to do a gajillion iterations, so 10,000 iterations. There's no reason to do a small number, right? You just do a whole boatload of iterations, and I'm going to keep going and keep going. But if at any point in time my approximate error gets smaller than this threshold, I'm just going to stop. Okay, so if I run that, boom, let's see how many points. It actually only did one, I don't know, do you call 0 an iteration? I don't know. It did n equals 0, 1, 2, 3, and 4. And then it got close enough. So if I crank up this sig figs and I say, hey, this needs to be accurate to like 8 sig figs, I'm guessing it might do a couple more. Because again, cosine is such a stable thing, so it settles into there. Let's go back to 4, run it, so it takes 4 iterations. And there you go. So that's kind of like the way the solutions, you'll see the solutions, that way totally works. It's not my preferred way, but it's a totally reasonable way, and I understand that everyone's welcome to do that. Now here's a slight tweak. Now, if you're to do it my preferred way, it says what it says right here. This is generally done with a while loop. What this for and if break, all this stuff is that is fundamentally doing a while loop. You want to, while your error is big, keep on going. So let's rewrite this with a while loop. Okay, so I'm going to change this. I'm going to say while, and while the absolute value of my EA is greater than ES. So you notice it's opposite of this, right? Because as long as my error is large, keep doing this, is what it's saying, right? So boom. So now I don't have to have this if break statement. So this isn't right because what's missing? So right now, so while the absolute value of this, I'm going to calculate all my things. Okay. So the first pass, last pass. The first pass through here, it's going to say, is the absolute value of EA greater than ES? And it's going to give me, let's look at this, we'll bring this up. It's going to give me an error. And that error is going to say, I don't even know what EA is. Why are you asking if EA is bigger than ES? I have never heard of that one before. So I need to initialize this to something. This is where my kind of cheat way is just to simply say EA is equal to 999. It's a number that's larger than ES, and so it makes life easy. It's also reasonable to say nan. So nan is not a number. The only problem with that is then I'd have to write this, and have to say if it's greater than ES or or does not exist EA. So I'm not a fan of that. So I'm going to stick with 999. It's not that EA actually equals 999. It's just that I want it to trip into this code. I want it to go into this code. So now I'm going to run this, and it's going to give me another error. So that error is n. N doesn't exist. So fundamentally, the difference between a for loop and a while loop is a for loop will create a counter, right? It creates this little counter that's going on. That counter doesn't exist in here. So n needs to be something. So in a while loop, you have to explicitly define it and increment it. So I can say n is equal to 0. So I need to start at 0. Why 0? Because this starts at 0. Some of them start at 1. They can start at 7. Who knows? It doesn't matter. You need to start where that starts, right? So, oops, wrong one. So there you go. And now I can do all my math, and now I need to come in here. I say n is equal to n plus 1. So now, boom, hopefully I can run it, and it just works. And it's the same answer. There we go. So there's the data. So this is kind of how I don't know, learned. This is my preferred method, a while loop, because it's in my mind it makes sense. While the error, so let's kind of think through this code. What is it saying? It says while the error. So what is this error? It's not really an error. It's a misnomer to call it an error. It's what we call it, and that's what we're going to keep calling it. But it's what's the EA is the difference between my guesses. So how much am I really changing on each step? Because if I am not changing on the step, there's no reason to keep going. Because eventually, if you look at the actual summation, you're dividing by 2n factorial. So this x to the n gets pretty big pretty fast, right? But the factorial gets big even faster. And so real quick, you're dividing something by a really, really large number, which functionally makes it 0. So each time you're adding something, you're saying this my next guess is my previous guess plus 0. And then my next guess is again my previous guess plus 0, and so on. And so you're going to have to, you start doing less and less important things on that. And so that is what EA is measuring, is percentage-wise, how much am I changing from one step to the next? Because eventually it's not enough that it's worth going. It's not worth continuing on. Now, if in here, one other thing you could do something like this. You could say if n is greater than 10,000, then break. That's a nice catch. Quite frankly, at this point, it's the same as it's the exact same as your for loop, just you did it kind of in the different order. I personally don't usually do that. So that's what I would go with. So there you go. So there is problem 411. Hopefully there's no like mysteries to it. Again, I would not try to just memorize the process. I would try to understand the concept. If you understand the concept, then you can kind of build up to what you need to have. There you go.